Next talk is by Robert Westerman, and we will stay in Aeolian environments. Yeah. Stage is yours.
Yeah, underground. Okay, so red for back and green for forward. Okay, so I've got a question for Joanna. So if you've got no crust at all, compared to crust, irrespective of rainfall and so on, does that make a difference? It does, okay, good. Right, so this all started at Herrick Watt. It was for reservoir model building, you know, in 3D and stuff. So then you start to ask the question, why are we getting ground radar reflections at all? You know, if you come from seismic and you're using ground radar to image things, you're thinking about impedances and you're wondering why. You get a reflection event. And in the case of radar, I can't actually see the screen. Up top left there, that's right. So it depends on moisture contrasts. Obviously, if engineers, they're after steel pipes and so on, but in sediments, it's have you got a difference in moisture? So that seems to be the key if you suspect that something's going on. And the reason behind it is that water's got a very high dielectric permittivity, something like 10 or 20 times your average soil mineral and so on. And Montmorillonite actually is even higher. And there's an interesting comment about Montmorillonite I saw, because I don't know anything about this subject, right? Well, not the clays and the minerals and stuff. Apparently, Montmorillonite can have an even higher... Montmorillonite stimulated respiration of a wide spectrum of bacterial species, and that's by Stotsky and Rem in 1966, Canadian Journal of Microbiology. So there's a sort of link-up between mineralogy, biology, moisture, and possibly the radar thing. So, and there's this nice phrase, microbial moisture niches. So maybe that's what I've got to fill this gap in, basically. Right, moving on. Right, so our sort of what we did was in 4 parts. Normally people just get radar and get a velocity and then make up their minds about what it means. But as coming from seismic, you would calibrate it against borehole logs, right? You actually drill through and ground truth what it is and do a synthetic and so on. So we've got 4 sort of sections. We've got the actual response itself, amplitude anomalies, which is getting onto a sort of rock physics thing. We've got some EM logs, sort of, for the first time. And we looked at the grain coatings belatedly. That's still going on, the grain mineralogy. Okay. Location. So we're in Oman, which is a fantastic place. Go there if you can. In the northern part of the Wahiba Sand Sea, this is kind of local base level, this wadi, which is an outwash fan from the Oman Mountains, which are up there, which is a massive overthrust that's mentioned previously. And I'm going to tell you about 2 locations, if I have time. One is in the far northwest, where the Dra are going onto basement. The Dra, these long megadunes here. And there's the white bits in between interdunes, which are sort of clay pans with a lot of calcrete. And this section here is down somewhere in the middle of the northern part of the Wahiba Sand Sea. And this is a cartoon of this seismic line here, going from south to north. And you can see that the accommodation space is increasing towards the Oman Mountains in the north. And also, we've got what Caroline is pleased to call, what's it called again? Yes, it's called geomorphic accommodation space, so it's above. And the thing is, you've got different base levels here. Here's the seismic datum, which is pretty much the same level as this Wadi Baha here, the outwash fan. But of course, mean sea level is about here at the moment. And during the last previous ice ages, and maybe the next one, it was right down here. So we're way above base level, except for very locally. And even there, we're about 80 meters up. Right. So this is in the far northwest, from Google Earth, of course. And we're looking north, and along the steep edge of the Dra on the west side, These are the folded basement rocks here with some calcrete in between. And you can see the seaf dunes, these long linear dunes coming along and then swinging in, you know, probably refracted by pressure effects into parallelism with the dune. And we're looking at the old draw here that the seaf dunes are migrating across and seeing what's in it, because we want to know for reservoir models, right? But as an aside, over on the coast, there's, this is from a fantastic book, beautifully written, you can see growth, what they call growth surfaces, geologists that is, and then bottom sets and so on, but nothing much more of the dunes. And this is supposed to be, I think, from the literature, Steve and Freiberger, and also the Permian Rock League and, in Poland, sort of dominates the usual view of reservoir models, that you don't get complete dunes, you just get the slippers left behind as they shuffle off to bed. Right, so back into the evidence, what we've actually seen. So the first thing that struck me in 2000, show my age there, 2006. That's curious. Why are these reeds sticking out the side of the dune? And then you've got these runnels coming down, stopping here. This is right on the top of the draw. But when we went back in 2009, I didn't get a picture because my camera battery ran out. I was standing in exactly the same place, and all this had gone. And we just got this rounded mound of stabilized dune, and these are actually growing in stabilized sand that's much older than this currently mobile sand. Okay, so I want to compare that with, this is a section through a 3D ground radar that we did the same year, at 500 megahertz. And notice this thing here, which you can track north-south at about 4 or 5 meters depth. It's at the limit of penetration. And sitting over the top, you've got complete dunes sets here. And they built a reservoir model of that as an MSc project. So a very similar situation, plausibly, I suppose. That's, I think, anyway, a claim to that. In other words, it's an ongoing process. Now, back in 2000, Charlie Bristow and, what's his name? Lancaster, I don't know him, but Charlie, they did these sections in Namibia. It's an interesting paper in Nature. And this is the longest and biggest of these dune sections that they provided in that paper. But they didn't remark on this here at all. So they've got all these reflection events, as had we, but they didn't comment on this dimming here. You know, why have you got the reflection events and why do they dim? Is the obvious question. And there's, you know, if there's a sort of version of the interpret, and I'm basically saying, well, here's that rounded mound again, and then the dune is growing as Charlie described, like that. And this is the seaf dune, you know, east-west going off to the north, I think. Right. So then then this is from our far northwest in that last year. And we've got all of these events here, and we've got some sort of dimming here. Now, the key thing is that both in Charlie's case and ours, I'll go back here, you've got the dimming, and the usual explanation with radar is that you've got conductivity and you've lost your signal because it's dissipated. But we haven't lost the signal because we can see a reflection event going below it. Now, it's cut off the section there, unfortunately. But we can see we've got this event here going underneath the dimming. So we haven't lost the signal, we've just lost the reflectivity of here. And again, in our stuff, we've got loads of this actually. We've lost the reflectivity here, it would appear, and the signal is still coming back from these deeper events. And again here, it's dimming here and here, and we're still seeing stuff underneath it. So, searching for an explanation, right? I'll show you later when I've got the calibration that actually the blue is positive, which should be damp over dry. So if I just use, this is image J, if I pull out the bigger damp over dry interfaces, plausibly. You can see that they sort of form, you know, what could be like umbrellas over the dimmed areas. Just speculative. And then Dominic did this fantastic he did several of these actually, 600-meter trek with the Ultra GPR, which is at 30 megahertz, but actually we lost frequency very quickly. And down, most of this is 12 megahertz. So quite low frequency. And the first thing you see is that we've got these sort of dim areas here. In the agricultural literature, you have a sort of wettability problems where there are fungi in the soil and the rainfall has to finger in. And I just wonder if these are sort of, you know, got hydrophobins in and the moisture is able to finger in through here. And that's a detail of that little bit there, which was quite close to the study area. I'm asking questions here, right? Of you guys. Right, this is to break between the radar bits that I'm showing you and the calibration. We only calibrated at 50 megahertz, and people assume that this is all frequency independent, but it isn't, in fact. Now we could actually measure it with this kit here, the full range. This is the Schlumberger logging tool here. I've never seen it used, but there is one. And these are the different frequencies that we have used on the 3 visits. So I got about 80 measurements. So this is just gathering some stuff in the study area, or the main study area. This is the mobile stuff at the surface, and then scraping that away, you can start an auger hole, and eventually you can dig a pit. You can see it stands free, and when you sit in it to do whatever you want to do, you can feel the dampness in the wall here, right? And but when you get to 1 meter down, you have to bring the auger out. It's terribly hard. It suddenly goes terribly hard. And Majid came out of the truck and gave me a hand to auger the thing. But when it came out, it ran out. So it's really curious what happened at 1 meter. All of the 80 readings that we got, if we did a principal components analysis in that passed that free statistical thing for paleontologists from Sweden, I think. You can see this trend for both imaginary and the real dielectric, which is this moisture parallel thing. So these 3, and then there's a separate sort of, possibly separate thing, which is related to the magnetic susceptibility. So sort of a moisture story again. Then plotting all the results for those 2 boreholes on a 1 graph. But so I'm just using a log scale here to say it all goes on 1 for comparison purposes. And you can see that from the surface, it gradually increases the moisture content from about, what's that, 2 to 4 or 5%. And then it drops back suddenly at this 1 meter. So this is the bit that's hard to auger. And then it starts to increase again. So it's a kind of wet over dry interface there. Interestingly, susceptibility, magnetic susceptibility just chugs on down. It's pretty, it's got another agenda, clearly. It might be to do with what they call siderophores, apparently, but you guys know that better than me. And the conductivity is trogging down here. There's a hint there that it might mirror this, which is what it's supposed to do. Fortunately, it's low and continuous, so that's why GPR works. What's next? Oh, yeah. So, unfortunately, that's got messed up. So, here's a model which... sorry, what's the wrong button? Here's a model which unfortunately has to be stepped because I'm using this free GPR sim here. There's a better solution from Edinburgh University, but I've never managed to get it to work. This is the pulse. You can measure this from the direct arrival anyway. It looks quite similar. So this is the synthetic here, and this is the local radar. And so you can see it's... okay, right. So you can see I've matched the... it matched it. Never mind, sorry. I better get on to the really important stuff for you guys, which is the next 2 slides. Jim has done some SEM work. So we've got this above the dry bit, the below dry bit, and in the next layer. And this is just a sort of mineralogy thing. And I can't really see a lot of difference. He's going to do more work on that. And this is a really interesting one, just in the dry bit here. And this is as far as we've got, okay? And this is where I would hope you'd say, oh, we know what's going on here. The calcite's interesting because the coarse crystals around the outside and the fine is in the middle. And apparently microbes do this. They don't let coarse crystals grow near them for cell description purposes, or not again. And then, of course, there's a relationship both in the detrital minerals and the way microbes partition, or would partition if this is true, iron from titanium. They don't want the titanium, they want the iron. And here are the clays. Now, that's really got reservoir significance, and it's adhering to the grains for some reason. There you go. So I think I can just skip the rest. That's to say people observe microbes around and stuff. And that's the end saying we begin to fill this gap in. And that's me. Okay. Cheers.